Welcome back to OGLDEV, guys. I guess by now you're already tired of the boring rotating cube, so let's turn it into a slightly less boring rotating texture cube. In fact, using textures on objects is one of the most basic techniques to increase realism in your scene. We call this technique texture mapping, and it has been in use in the 3D world for years. There's even evidence of it being used by cavemen some 30,000 years ago. Seriously, the technique has been invented by Edwin Catmull in a well-known paper from 1974. By the way, this guy went on to co-found Pixar. That's interesting. Back to texture mapping. The challenge here, of course, is to make the image or the texture stick to the surface of the triangle. So regardless of the orientation of the triangle towards the camera, the view of the texture remains consistent. This includes handling of perspective issues when one side of the triangle is very close to the viewer while the other side is further away. The solution is to attach texture coordinates to each vertex and have the rasterizer interpolate them across the triangle face. So every pixel on the screen gets its own texture coordinates based on its relative proximity to the three triangle vertices after they have been projected on the 2D window. The fragment shader uses the interpolated texture coordinates in order to sample a pixel from the texture. By the way, the texture pixels are called texels. The texture coordinates are normalized. Therefore, coordinate 0, 0 matches the bottom left-hand texel, and coordinate 1 by 1 matches the corner on the opposite side. In order to calculate the size of a single texel, we need to divide 1 by the width and height of the texture. Here we can see a 2 by 2 and a 4 by 4 textures. The width and height of the corresponding texels are half and 1/4, respectively. The number of axes in the texture coordinates depends on the type of the texture. In this video, we are going to discuss 2D textures only, since they are the most common type of textures. In a future video, we will also meet 3D textures that can be used for the skybox technique and cube mapping. There are also 1D textures that are basically arrays. They can be used to sample various values into the shader, but in most cases, these will not be irregular images because an image with a single row is not very interesting. You can name the components in your texture coordinates as you wish, but the OpenGL spec calls the axis that goes along the rows of the texture S, and the axis that goes along the columns T. If you're using a 3D texture, then the third axis is called R in OpenGL, but again, this is up to you. Another common trio which is often used is U, V, and W. Whatever you do, make sure to remain consistent. The most trivial case with texture mapping that can be thought of is when we have a quad of two triangles that after projection turned out to be exactly the size of the texture. In that case, we have a one-to-one mapping between a pixel and a texel, and we will render the texture perfectly, exactly as if it was opened by an image viewer. However, this will rarely happen in real-time rendering. Since the scene is probably dynamic, with both the camera and objects moving, the triangles are not going to end up looking so nicely as in that quad we just saw. We will get all sorts of triangles, so the perfect pixel-texel matching will simply not happen in most cases. In addition to that, we are probably going to end up in one of the following cases: minification and magnification. Minification happens when a textured triangle moves away from the viewer in the 3D world. As the projected triangle grows smaller, we have less and less pixels to render, while the texture remains in the same size. This means that we might skip some texels. For example, if the width of the projected triangle is 64 pixels while the width of the texture is 128, then we are going to skip every other texel. Remember that the texture coordinates are constant vertex attributes, but if we need to interpolate them over a smaller number of pixels, then the delta between the texture coordinates of neighboring pixels will be larger. Magnification is exactly the reverse. As the triangle becomes closer to the camera, its projected size grows larger. Using the same example with a texture with 128 width, if the width of the projected triangle is 256, it means that we have 2 pixels per texel. In this case, we can't achieve a high fidelity with a rendered triangle unless we use a larger texture. More on this later. The process of choosing a color for a pixel through texture mapping is called filtering. we can set different filter types for the two cases of minification and magnification. The most common filter types are nearest and linear. When we use the nearest filter, the texel that is chosen is the one whose center is closest to the texture coordinates of the fragment. This method performs faster, but the visual results may not be that great in some cases. The more capable linear filter is most likely slower on most implementations, but the visual result is expected to be better. Here, the GPU will perform a weighted blend between the neighboring texels. For example, if the texture coordinates end up exactly in the middle of a 2x2 texel quad, then the GPU will take 1/4 of the color of the 4 neighboring texels and sum up the results to get the final color. Naturally, as the texture coordinates get closer to one texel, the weight of its color will grow at the expense of the other 3 texels. Texture mapping is a big topic, and there are more features available to it in OpenGL, but at this stage I'd like to continue to the implementation. We will address these features in a follow-up video. Let's understand how the theory of texture mapping actually works in OpenGL. We basically have 3 entities that are working together. We have a texture object that contains the texture image itself. You can create many texture objects, and as far as I know, you're only limited by the amount of memory on your machine. However, you cannot make all these textures available to the shader at the same time. And the reason is that we have something called a texture unit that sits between the shader and the application code where the texture objects live. We connect the texture object to one side of the texture unit, and on the other side the shader samples from the texture unit. So the shader doesn't know anything about the texture itself, and between draw calls we can replace the textures and use the same shader again to sample from the new texture. As you can imagine, a single texture unit would be quite limited, so OpenGL provides us with an array of texture units so we can access multiple textures from the shader. The number of texture units may change from one GPU to the next. High-end GPUs may contain more texture units than their lower-end counterparts. You can query the number of texture units on your system by calling GL_getIntegerV using the GL_max_texture_image_units in the first parameter and the address of an integer for the result in the second parameter. On my GPU, I have 32 texture units. This code is not required to get texture mapping working, but it's nice to know the capabilities of your system. So we have a texture object and a texture unit, and the third entity is the shader sampler. The sampler is a uniform variable, so in essence, it is similar to other uniforms that we are already familiar with, such as vectors and matrices. The job of the sampler is to provide an interface to the texture unit. As we shall see shortly, GLSL provides us with special functions for texture sampling, and these functions need to know which texture unit to access. The sampler uniform variable is updated by the application with the index of the texture unit. The shader accesses the texture unit through the sampler uniform variable and reaches the texture object that was bound to the texture unit by the application. Now let's quickly go over the steps required to get texture mapping working in OpenGL. First, we need to load the image data. There are many options here, including loading the data with your own custom code or using a third-party library, and there are many libraries available. We will be using STBimage, which supports many file types. It is very popular and easy to use. Next, we need to generate a handle for the texture object. This is very similar in concept to creating other OpenGL objects, such as buffers, shaders, and shader programs. We need to bind the texture object to a target. This tells OpenGL whether the texture that we are creating is 1D, 2D, 3D, etc. Now comes the time to load the texture data from the CPU memory into the GPU. After that, we configure various texture-related configurations such as minification and magnification filters. At this point, our texture object is ready. We can now go ahead and make one of the texture units active. This tells OpenGL that we are going to configure this unit. We bind our texture object to the same target as before, and OpenGL performs this operation on the active texture unit. The shader must include the sampler uniform variable and a function to sample from it. We need to get the uniform location as usual and configure the index of the texture unit we want the shader to access with that sampler. Now comes a very crucial step. We need to populate the vertex buffers with texture coordinates. In a real application, you would assign texture coordinates to all the vertices using the advanced tools that 3D modelers such as Blender, Maya, and 3ds Max provide for this purpose. We're going to address model loading in a few episodes, so for now we will simply create them manually just as we created vertex positions. To make sure OpenGL can read the texture coordinate attribute correctly, we need to define the layout of the vertex buffer and enable this attribute. If everything went well, our texture should now be visible. Now let's review these steps in the actual code. First, we need to get the STB image library and make it a part of our project. The nice thing about this library is that it is self-contained in just one big file. You have several options here. If you've downloaded my sources, you can find this file in OGLDEV/include/thirdparty/stbimage.h. This file contains the latest version at the time of recording this video, but it may not be always up to date as the original Git repo. Therefore, you can also access the file with your browser using the link I provided in the video description. Click on Raw, right-click and select Save Page As, and save it in your project. In order to make this header accessible by the application, you need to add the proper include directive to the compiler. Since I've already got an include directive for my main include directory, I've used include 3dparty/stbimage in my application code. This brings us to the next file that we need to create. It's a very simple CPP file which I named stb_image.cpp. I created this file in OGLDEV/common/thirdparty and included it as part of the build command. In this file, we just need to define the preprocessor macro stbimage implementation before we include stbimage.h. So the stbimage functions will be compiled only when this CPP file is built, but we can include stbimage.h and access STB functionality anywhere in our project. I've also defined the optional macro stbi failure user message to get slightly better error messaging. Before we dive into the details of texture object creation, I want to show you a very simple class that I've created in order to wrap the texture loading functionality outside of the main application code. This class is called texture and it is defined in include/OGLDEV_texture.h. It provides three public functions: a constructor that takes the texture target and the texture file name, a load function that we need to call once in order to load the texture from file and populate the texture object, and finally a bind function which makes this texture active. If we're going to use a single texture, then we only need to call this function once, but if we plan to switch between textures, then on every switch we need to call bind in order to make a new texture active. We also have three private attributes here for the texture file name, the texture target, and the texture object. You can also see here the remains of the old code that I've used on my website in the past. This code uses ImageMagick instead of stbimage. You can explore it further by commenting in Use ImageMagick, but in this video I will stick to stbimage. Now let's see the implementation of the texture class. First, we include the stbimage.h header. This should match the location of this header in your project. Next comes the constructor, which simply stores the texture target and the texture file name in the attributes. In the load function, we start by calling stbi setFlip vertically on load with 1 as the parameter. The reason is that stb loads images by default from top to bottom, while in OpenGL the texture space goes from bottom to top as we saw in the background section. Next we call stbi load in order to load the texture from file. This function takes the file name in the first parameter. You can see that I'm using the cstr function on the std string in order to get the string as a const char pointer. After the file name, we have the addresses of three integers for the width, the height, and the bits per pixel of the texture image. We need these to tell OpenGL the dimensions of the texture. The last parameter allows you to choose the number of image channels to actually load. Set this to 0 to load all the channels. If the call to stbi load is successful, we should get the address of the texture data as an unsigned char pointer. Now, if you were Chuck Norris, you could simply continue. You are not Chuck Norris, so make sure to do your error handling by checking for a null return value. you can get the error message by calling stbi failure reason. The next step is to generate the texture object by calling glGenTextures. This works the same as other GL APIs, such as glGenBuffers. We specify the number of texture objects that we wish to create and the address of an array of uints to get the handles of these objects. In our case, we create a single object and we store it in a class member. Next, we bind the newly created texture object to a texture target. This is very important because it tells OpenGL whether we're going to create a 1D, 2D, or whatever type of texture. Remember that the target was a parameter to the constructor, so we have it as a class member. We can now load the texture data into the texture object. As you can see, right now this class can only handle 2D textures and there will be an error if it is used for other targets, which we will handle in the future. To load 2D textures, we use glTextImage2D. This function is quite complex, so let's review it one step at a time. The first parameter is the target, glTexture2D in our case. The next parameter is the MIP levels. I won't talk about MIP mapping in this video, so just use 0 here. Next comes the internal format of the texture, which is how you want to store it on the GPU. It may be stored in a different format than the original image. As you can see, the number of options can be quite daunting and in some cases can cause quite a headache. For now, we will stick with glRGB because we're loading a standard image with 3 channels. Next, we have the width and height that we got from STB. No problem here. After that, we have the border, which must be 0. Okay. After the border comes the format of the original image and its data type, and again we have several options here. For example, you can load an RGB image where each component is a float that goes from 0 to 1, or an unsigned char that goes from 0 to 255. Based on our knowledge of STB image, we use glRGB and glUnsignedByte. For a more general purpose texture class, we may need to extend this functionality, but for now it will suffice. Last but not least comes the pointer to the actual texture data. Next comes a series of calls to glTextParameterF to configure the minification and magnification filters, as well as the wrapping modes. I suggest that for now you simply copy this code as is, and we will delve into the possibilities that these options provide in a follow-up video. The final GL call in this function is glBindTexture to the same texture target with 0 as the texture object. This unbinds the current texture object to make sure that future configurations of texture-related stuff does not affect our new texture object by mistake. Before leaving this function, we also released the memory that was associated with the image by STB. The image is now loaded into the OpenGL runtime, so there is no point in keeping an extra copy of the original image in CPU memory. The last function in this file is bind, which takes in a texture unit, activates it by calling glActiveTexture, and binds the texture object to the same target on that unit. In a simple application with just one texture, you only need to do this once, but in a complex application with multiple texture units and texture objects, you must make sure to set up all the units correctly before the draw call. Now let's see the changes in the shaders. In the vertex shader of the last few tutorials, we actually had a second input attribute for the color. This is now replaced with the texture coordinate, which is a 2D vector. We have a matching output attribute, and all the vertex shader needs to do is to pass it along to the fragment shader. Remember that the rasterizer will interpolate this as any other attribute, so the fragment shader will be invoked with the texture coordinate that matches the current pixel. In the fragment shader, we have a matching input attribute for the texture coordinate and the uniform variable of the sampler 2D type called gSampler. In order to set the output color of the fragment shader, we call the internal GLSL function texture2D, which samples the value from the texture unit whose index is configured into the sampler. The second parameter to texture2D is of course the texture coordinate. Makes sense. Now let's jump into the application code and make sure that we are getting the uniform location of the shader sampler. Right here. We will later see how this location is being used. Let's see the modifications in the vertex buffer. In the vertex structure, I've replaced the color attribute with the texture coordinates, which is a 2D vector. In the createVertexBuffer function, I prepared a set of 2D vectors for the 4 corners of the texture, and I simply threw them on the vertices one by one. So we have the 4 texture coordinates here, and then here. So the result will not be perfect on every side of the cube, but I hate working manually with vertices like that, and we're going to have a model loading code really soon, so why bother? Before we jump into the last step, which is in the render loop, let's just review the remaining changes in this file, which is mostly about the texture class. First, we have a pointer to the texture class and the location of the sampler in the global section. We already saw that we're getting the location of this sampler. In the main function, we allocate a new texture object by passing in the target and the file name of the texture file. Next, we call the load function of the texture class. As we already saw, this triggers a series of OpenGL calls for generating and populating the texture object. And this is mostly it. Now let's see the render function. Here we're calling bind on the texture class with GLTexture0 as the texture unit. This activates the first texture unit and binds the texture object to it. Next, we set the sampler uniform variable to 0. Notice that this is the actual 0 index and not the enum GLTexture0. Since we had position and color before, we already have 2 vertex attributes enabled. We just need to make sure to set the texture coordinates layout to 2 floating points. Now let's build and run the code. So that's it for now. We will explore more advanced features of texture mapping in OpenGL in a follow-up video. If you enjoyed this video, please hit that like button and subscribe. You can also support my channel at patreon.com/OGLDEV. Thank you for watching, and I will see you soon.